All right, Paul, this relativity stuff's pretty interesting, but I thought we were going to be talking about black holes. And I know black holes involve relativity, but I also know they involve gravity. So how does this all hang together?
Well, to put gravity into this whole relativity picture, we're going to have to introduce a new type of diagram, what's called a space-time diagram, because it includes space and time, curiously enough.
Ah, I see. So we've got the x coordinate and the y coordinate, and we don't have a z coordinate.
Yeah, because in reality, space is three-dimensional. You've got x, y, and z coordinates, and then you add an extra dimension of time, it becomes four-dimensional. At that point, your brain dribbles out of your ears.
Yeah, I don't deal with four dimensions very well.
So what we've done here is I just forgot about the fourth dimension. We're just, for purposes of simplicity, just have two space dimensions, x and y, and we'll have t vertically.
I see. So if you are here at the origin, then I've got a little bit of an x and a little bit of a y, so I'm here. And then I'm standing still and moving forward in time. So I'm moving up in time because I'm not doing anything. I'm continuing to exist.
Yep, so a stationary object is just a vertical line in this diagram. So you are moving through time, no one can help doing that,
Yep.
but you're not moving in space.
Okay.
But let's say
Simple
we
enough.
add a line like that. So what's going on here?
Ooh, so this time it looks like I'm moving forward in time, but I'm moving in the x direction and then back. So that's sort of me doing this.
And then coming back again.
There we go.
Yeah. So if something's moving, you get a slope. In this case, it's a slope this way, because you move that way. So your x is increasing while time goes up, and then you come back again.
Okay, fair enough.
Okay. How about that?
Oh, that looks like I'm going to have to be acrobatic. So that looks like the same basic idea, but I got to move a lot more and then come back. So it's going to be like,
Yeah. So you've got to move and come back at the same time you were before, but the change in x is bigger, so you're moving faster.
okay,
So in general, any sort of curve like this, slope indicates speed, and the bigger the slope, the faster you're going. And that leads to the idea of the fastest thing of all, light, as we've just been talking about. And the idea that, let's say there's an event down here at the bottom of the cone, and let's say it flashes out light in all directions. Now light will be going at a 45-degree angle in this thing, if you use a scale the coordinates correctly, and so there'll be a cone, which is where the flash is, a hollow cone. So if you're anywhere on this cone, you will see that flash. If you're further out, then the flash won't have reached you yet. If you're further in, the flash went past sometime in the past.
okay. So that means, just to get our heads around it, we start off at a flash here, and then a very short time later, so for example, if I shot a light off right now, you're about 2 meters away, okay? So that means a few nanoseconds. There's this little circle that everyone can see that flash for that very short period of time. And then as each moment in time moves forward, that circle goes further and further out. And so you get, in this time, space-time diagram, this cone out. Okay, I think I've got that sorted.
Okay, so what this also means, of course, is because you can't travel faster than light, it means anything outside the cone cannot be influenced by an event down there at the base of the cone. So no matter what happens there, the biggest explosion, the most, I don't know, anything what you can imagine that happens down there can have no effect out here, because even at the speed of light, it can't get that far. Anything inside the cone could in principle be affected. If it's actually on the cone, light could affect it, but if it's inside the cone, it could be the light comes out here and then bounces off a mirror and hits it, or you leave a video cassette that drifts upwards here and then sends a message out at a later time, or you actually fly a spaceship there. So basically, only things inside can be influenced. Only the place inside the cone is where you can go, because it only goes slower than light. So you've got to be somewhere inside this cone, no matter how good your rocket is.
Okay, so that cone is almost like what we would call in astronomy a horizon, where you really can't get past, even no matter what you do.
That's right, it is a horizon. So it's saying the only thing that can be influenced by that point is in here, or if we are up here at a later time, if we're inside the cone, we can see what happened down there.
Okay. So now let's add some gravity. Now what happens?
Well, the idea is that gravity tilts the cones. So let's imagine this blue line is something heavy, star, neutron star, whatever it might be, and we've got a whole bunch of cones from a whole bunch of different events in a grid all over the place. So out here, a long way away from this mass, the cones are vertical as normal, so things can go in any range of directions along like here. When you get closer, you see these cones are tilted over, pointing towards the mass.
And that's sort of because gravity, the way we think of it through Einstein's version of relativity for gravity, we're sort of warping the fabric of space, and so the cones fall over a bit depending on which way space is bent.
That's right. In Einstein's theory of general relativity, which we'll cover again in the cosmology course, what happens is that gravity warps space-time, and that has the effect of causing these cones to tilt over. Though we'll go back and do far more of that later on.
Okay.
So if you're here, your natural motion will be down the middle of the cone, which will bring you in, it's called falling.
Yep.
But you still have a choice. You can go at the speed of light, so you can still escape in that direction or that direction. But if you make the mass really big, you tilt the cones over further.
Ooh, so now this is kind of interesting because these cones right here are more than 90 degrees over, which means all directions, no matter how fast I travel, I can't get back away. I'm stuck.
Yep. So you take one of these cones over here, and your choice is basically you can't stay where you are because only the cone further in is possible. So your choice is you can only go in slowly or go in very, very fast, but nothing you can do will cause you to stay where you are.
So that means that nothing I can do, even if I'm light, I can't get away from this mass moving forward in time. Now that's beginning to sound like a black hole.
It is indeed.
Aha!
You remember we talked about the original idea of a black hole as being like a normal star with a normal surface and the light would just come up and go down. We're now seeing a rather different picture where the light it's emitted will go down right from the moment it's emitted. And also the matter can't sit there because matter can go slower than light. So everything has to move in. Its state of rest is to move in faster and faster, but no matter how much it struggles, even if it struggles away at the speed of light, it's still sitting on one of the cones here and it still has to go in.
Okay. So, all right. So these black holes seem, I guess I get with this, how these light cones and curved space all come together. I guess one could imagine maybe thinking of this in terms of how big they might be.
Yeah, it seems to suggest they can't have a size because the stuff has to go in and there's no stopping it. It's not as if the light cones suddenly start pointing upwards again. Then as closer you get, the more they're tilted over. So they can't seemingly have a solid surface. The matter must go all the way down to zero size.
Wow, that's hard to imagine, hard to visualize. We'll have to think about that.